Okay, we're going to get started. Good afternoon, everyone. Welcome to Progression's webinar featuring our simulation packages. Just a reminder, if you're just joining us, you can use the webinar control panel to raise your hand. You can also ask questions. There's a group box for questions and a little chat box. I've also uploaded 3 files in the handouts group box, and hopefully you should be able to download those as well. So anyways, welcome to our webinar. This one is especially exciting because today we have some key leaders presenting to us from 3DS or SOLIDWORKS Corporate. We have Dana Parrish, our territory sales manager, and also Ramesh Lakshmipati, our senior territory technical manager. So both are specifically managing the simulation product lines. So these two guys are simulation machines. I have yet to stump them on a simulation question. Today they'll be presenting some actual case studies with very familiar design dilemmas. These are scenarios that you have probably already encountered in your role, or it may be in the horizon soon. Like a simple example is a part fails in the field and your boss brings it to your desk and says, okay, this part failed and we need to know why it failed and we need a new part and a better part. So that's pretty much a typical scenario. So this presentation isn't a rundown of how to drive the software. That's not what your job is about, and we have training classes for that. What we want to do today is to show you how you can use the simulation toolkit to approach these real projects that you have on your desk right now. We're going to answer the questions that you would have during the progress of your design, and beyond just making a functional, reliable part, a better part. We're going to show you how you can save and make money instead of spending it in areas of the design where it isn't adding value. We're going to show you how to use simulation to make confident design decisions and ultimately design the best part. So just a reminder on how to use, real quick, we do have a hot simulation promo going on right now. With each SOLIDWORKS premium license purchased, you can get at no cost a simulation professional. And you'll see in one of my handouts what that includes. It includes frequency, buckling analysis, optimization, drop tests, several other things. Or you can get a plastics standard package. So feel free to ask us more about that at support@progressiontech.com. Look over to your webinar control panel on the right side. You can use the little red arrow to collapse it or expand it. And then you might have noticed some of the group boxes below. Feel free to use those. And then also enter questions in the questions group box as you have them. And then Dana and Ramesh will answer them. Or I will. Okay. And so now I'm going to hand it over to Ramesh.
All right.
Oops. Is Ramesh showing his screen? There we go.
Yeah, there it is. There it is. And good afternoon, everybody. This is actually Dana Parrish, but Ramesh will be driving the slides, and then I'll turn it over to him. And so on behalf of SOLIDWORKS, thanks for taking time out to come and learn about our simulation tools, how to save and make money. We're gonna be presenting some scenarios for your thoughts. And again, like Ami said, if you have any questions, comments, please enter them into the questions field. We'll try to answer them. Ami and I may answer them while Ramesh is doing it. We may answer them on the fly, or if they're really good questions for everybody, then we will hold out till the end to do that. So we want to go ahead and we'll get started, and we'll dive into this. So go ahead, Ramesh. So this is a typical alternative, or a typical development process that's out there today, right? I think everyone understands this process as it is, where you have an idea that's come up, or some sort of your customer or end user has a need. something that needs to be looked at and developed and perhaps at that point made, produced, and sold. So you take that concept, and then from there you then put the detail behind it. I call it the engineering meat behind it. Then you build it, prototype it, create the communication, and then out it goes to manufacturing. A typical serial line process. What we're showing today is kind of how simulation, especially as part of the overall development process with other tools, can be used up front during the detailed product design process, where changes are easiest to make and cost the least amount of time and money. And because you're doing it up front, in this area where you can make very quick changes and you can see things in action, see your model virtually, your design virtually before ever prototyping it, you're going to A, eliminate unnecessary prototypes, and B, make better business decisions and design decisions moving forward. Go ahead, Ramesh. Ramesh, you want to hit the slide? Yeah. Oh. We're stuck. Are we stuck? Or is it me?
I can't hear Ramesh yet.
I'm here, Piyush.
Oh, there you are.
We're actually on the slide that says navigating to the best design.
I'm not even, okay, I'm not, I must have a lag on my end.
Oh, okay, got it.
Okay, no problem. I know exactly what slide it is, so I'll just talk about it. So what we have here is, a lot of times is that, we look at back in the old days, it was, you had, and I'm an older guy, and hey, there it is. I have a big time lag. It just popped up. My apologies for that. I have a lag on my end, big time. So in the old days, if you want to get from point A to point B, you used a map and compass, and you whipped the map out. I remember as a kid going, when I lived up north, I'm in Florida now, driving down, you always had the big map out, and you're always getting lost, and you think you're taking a right when you're taking a left, and you end up at point B, but it takes some time. Things are kind of crazy, but you do get there. And with simulation, it's kind of like having a GPS now for your design. Think of the simulation as a GPS, because now GPS is going to get you there very quickly and right to the point. And you know exactly what's going to happen. You know when to turn, when to stop, where to go. If you miss the street, it's going to recalculate for you and get you there. Simulation's the same way. If you're making a design mistake, it's going to help you find that design mistake and get you from point A to point B. So think of simulation as a navigation tool. It's helping you navigate to the best design. It's like when you do a design, you turn on your GPS and let it do the job for you. Go ahead, Ramesh, next slide. Hopefully I don't have the lag. And so along that, and now it's back. Look at that. Now I'm back to normal speed. So along with that navigating the best design, it's in a sense, say you're going across town, you may want to stop at different waypoints along the way to the final design. Those waypoints may include, for your design, safety, durability. Is it kind of lightweighted? Do I have some sustainable, perhaps, initiatives with my company? Is it comfortable? How about any type of fluid or cooling? So again, you're going across different waypoints to the final best design. And we have the tools that will answer all these types of questions. Is it safe? Is it durable? Comfortable, lightweight, sustainable, whatever is important to you as an engineer and designer to come up with best design. There are tools within our tool set, and you're going to see them in just a minute, that are going to help you answer these types of questions. Go ahead, next slide. So we're going to take a very quick design sprint. We've got 3 real-world opportunities here that we're going to talk about, and I'm going to turn this over to Ramesh in just a second. So the first one is going to be a wheel rim. This is from a real customer. The customer issues had to do with strength, optimization, and durability. And by optimization, I mean, it's a wheel. It's for competitive racing. It's for automotive. It has to be light, durable, strong. All these things have to happen at the same time. How do we do that without having to build prototypes over and over again to hone in on that best design? Then we're going to talk about a platform for a riding lawnmower. If you ever see professional guys with the professional tractors and lawnmowers, they have the big platform they stand on, so they have to walk with it all the time. And a lot of times there's all sorts of issues now with vibration and comfort level and making sure that it stays strong while this thing's being beat up and shaken up and thrown around by the lawnmower. And then our final example is going to be having to do with more of our flow tool and making a design decision based upon thermal characteristics. You have this electronics enclosure, and because of it, there's heat being generated. And you might want to ask questions. Do I need a fan to help air go through it? Can I get away with just the ambient air? And if it is ambient air, do I have a full enclosure, or should I put slots or holes on it to help the air get through and out, making it very efficient and keeping it at a certain temperature? Again, keep in mind these are real world items that we've gotten from our customers, and so these are design decisions that they've had to make every day. So with that, I'm going to turn this over to Ramesh. Again, Ramesh is our territory technical manager, who makes really makes a really great thing with SOLIDWORKS and simulation. So Ramesh, I'm going to leave it to you. And again, if you have questions, please type them in the field and we'll start answering them, or we'll hold them till the end. Ramesh, it's all yours.
Thanks, Dana. Thanks, Ami. Can you guys hear me okay?
Yes.
Hear you fine. Perfectly.
Perfect. All right, so we're going to get started with the first design challenge, which is wheel rim assembly. And this actually comes from one of our customers, Full-Time Motorsports, based out of Dayton, Ohio. And so one afternoon when we sat with them, trying to understand what the key challenges are, so here's what they were actually telling us. Prototype testing was expensive and time-consuming. The competition was actually, more. They had a lighter wheel rim, and they're actually losing market share to the competition. They also were interested in understanding how a tool like SOLIDWORKS simulation can actually help them, predict the durability or the life of the design of these rims. So I'm going to actually break this demo into 3 different segments. First is we're going to look at, trying to understand, what the strength of this design is. And then we'll dive into tools like design optimization to see how SOLIDWORKS simulation offers a completely automated way of, trying out multiple design iterations. And once we get to, let's say, an optimal or the best design using design optimization, we'll test that optimal design for durability. And so that at the end of the day, we are able to paint the full picture going from point A to point B on the design. So with the strength test, a simple criteria that we are after is the factor of safety or the strength of this wheel rim should be at least a 1.5. So in terms of, setting this problem up in SOLIDWORKS simulation, it's pretty straightforward. Let's say, for example, we know a few details about this wheel rim. So the material of the rim is aluminum 6061 alloy. And let's say, in the real lab where the physical prototype is being tested, they actually, Forge Line just goes ahead and fixes the back end face of this rim, and then they apply an axle face condition as shown here, and apply a maximum load of 2,900 pounds, which is kind of in the worst case scenario in a cornering situation. Remember, like, these wheel rims actually go and sit in a sports car, so they won't actually simulate the worst case scenario of loading on the axle to understand, if the axle is going to transfer that load to the rim and if that rim is going to be able to withstand that load. So let's go ahead and take a look real quick in SOLIDWORKS. Okay, so here's a wheel rim assembly. Let's say it's completely designed top-down in SOLIDWORKS. And that's really the first step before you attempt to do simulation, because the simulation tools are actually built and integrated within SOLIDWORKS. So once you have your design ready in SOLIDWORKS, you can go ahead and say, I want to start a new study. And you can give that study a name, and depending upon the performance you're trying to understand, you can select one of the different types of simulation. So it could be something simple as linear statics for strength, or it could be thermal analysis for any kind of heating concerns, or frequency analysis for vibrations, and so on. So it's a simple selection to tell the program what exactly you're trying to do. And that's about it. Now, once you click OK, you get this feature tree, which has the same workflow, look and feel as the SOLIDWORKS feature tree. So you can follow a top-down approach for the simulation feature tree. So let's do that here in this demo. Now, this wheel rim assembly has 2 different parts. One is the axle. And what I've done here is I've made the axle rigid. So I don't really care about looking at any kind of stress or deformation on the axle. So I'm going to go ahead and make that rigid. Now, what's nice about SolidWorks simulation is the fact that, when you're dealing with assembly of different parts, you can tell the program what parts of the assembly are actually of interest when it comes to simulation. So that way you can say, all right, even though this is a part in this assembly, I want to exclude it from the analysis, or I want to actually fix it, I want to make it deformable, or I want to make it rigid. So again, depending upon what exactly you're trying to accomplish, you can go ahead and choose the appropriate options. Now, our design part is the rim over here. So that rim is going to be assigned a material, 6061 alloy. Now, what we do is we provide you with a database of different materials to choose from. And the good news is, as a user, you can also custom define your own material properties if the need be. So in this case, it's a simple 6061 alloy selection, and that's about it. So again, a nice way to kind of assign materials of interest to different parts of your assembly and go from there. Now, if I come down this feature tree, you can see that I have some fixtures, and fixtures is nothing but a great way to tell the program what the physics looks like and how is this wheel rim held in place. Now, what Forgeline told us was, well, we just grab the backing face on the rim and fix it in space. So that's exactly what this fixture actually does. It's called fixed geometry. And notice that there is a nice animation at the top showing us, if that's the appropriate fixture to use on that geometry. So again, a very nice way to make sure that, when we are setting up the problem, are we doing the right things or not? The animation might be a simple thing, but it goes a long way in terms of reinforcing, the appropriate physics of the problem. Now, you can also look at some advanced fixtures like symmetry, cyclic symmetry, on flat faces, cylindrical faces, and so on. So just keep that in mind. There are several types of fixtures, and depending upon how your design might be constrained in space, you can use one of these fixture options. The other fixture is applying more like a shear condition to the back face of this axle. So all we're doing here is we are grabbing that face and saying that face cannot move in the normal fashion, but it can actually move sideways. So it can slide, but it cannot move normal to that selected face. So more like a shear action that we are trying to simulate on this axle face. And the last thing that we're doing here is applying the load. And with SolidWorks simulation, you can apply different types of loading. So it could be a force, or a torque, or a pressure, gravity, whatnot. In this case, we clearly know that Forgeline is applying a force of about 2,900 pounds as the worst case scenario of loading. And you can basically see that I'm grabbing that face on the axle, and I'm choosing a reference direction. So in this case, I'm choosing a reference plane. And that reference could be anything. It could be a reference plane in SolidWorks. It could be an axis. It could be a coordinate system. So depending upon in what direction you want to apply the force, you can choose the appropriate reference entity, and then with respect to that reference, you can say in which direction you want to apply the load. And here it's about 2,900 pounds, normal to that selected reference plane. That's pretty much the setup process. Okay, so it's not rocket science. If you know how to use SolidWorks, you pretty much know how to use simulation when it comes to setting up the problem. Now, once we set it up, we can mesh and run the analysis. And here's what the mesh looks like. Just in the interest of time, I'm not going to actually show meshing process live, but you can see what the mesh looks like. This is kind of the default mesh setting, and it does a pretty good job of capturing the geometry for simulation, solving all those complex mathematical equations behind the scenes. Now, once you mesh and run the analysis, you have access to some key results. And these results are fully customizable. So for example, I can look at things like one meter stress, I can look at displacement, I can probably look at factor safety, and so on. So here, based on this baseline design, and based on the physics that I simulated, the wheel rim factor safety is about a 2.09. So that's kind of, making sure that the strength of this wheel rim is not compromised. So let's say we are after a factor safety, a minimum factor safety of 1.5. The program comes back and says, look, it's about 2.1, and that ensures that the strength is there in the design, but at the same time, it's also telling us that maybe we have over-designed this wheel rim. Maybe these ribs over here on the front end can be actually made a lot thinner, and maybe that will, still keep the performance or the factor of safety intact. So it gives us some rough idea about, what the existing strength is and what next steps we might actually want to take in terms of, modifying the design. So factor of safety is one thing that we're after. But I want to actually talk a little bit about what is called as a design insight plot. The design insight plot is a great way to understand how the load is being carried in the entire design. So you can see that all I have to do is drag the slider, and you can see that it's a simple blue and transparent areas representation. But what this means is wherever you have transparent areas, you don't have any kind of loading in that area of the design, which means I can trim or take out excess material without compromising on the performance. So wherever I see the blue areas are the areas where the load is being carried in the system. So this is a very powerful tool to use to quickly make a decision where in the design I can remove material without compromising on the performance. So let's go back and recap real quick. We looked at factor of safety. That's about a minimum 2.1, which is good. And we also looked at the design insight part, which is a great way to quickly understand where in the design I can take away material, and maybe that in turn is going to help me lightweight the design. So at this point, I can go ahead and start playing with the design dimensions, maybe change the thickness of the rib, maybe change the angle of spacing between the ribs, and so on. And I can spend the whole day trying to do that. But just to recap, we just did a quick strength analysis to verify if the 2,900-pound static load is a safe operating load. We got a good idea about the factor of safety. But now we want to actually go ahead and take this to the next level, which is to look at design optimization. How can we lightweight? So far, we have gotten some idea about, where we might actually want to focus on to remove material like the ribs and the spacing. And but can we do it in a completely automated fashion? That's what optimization is going to help us accomplish. So we want to design, obviously, a lighter rim. And so now we can either increase or decrease the rib spacing, maybe increase or decrease the rib thickness. At the same time, we want to make sure the factor of safety of the design is not compromised. It's a minimum 1.5 year after. So optimization is a great way to automate the process of testing multiple design scenarios or design iteration. And what you do here is 3 simple steps. The first step is, what are we trying to change, and how do we want to change it? And what's the performance we are after? So in this case, it's as simple as saying factor of safety should be a minimum of 1.5. And what's the ultimate objective? Well, we want to minimize the mass. So 3 simple steps is what is required to set up the optimization. And let simulation take over and do all the hard work behind the scenes to test out all the multiple combination of dimensions that will eventually get us to our goal. So here's how it actually works. This is kind of, optimization interface that you're going to be dealing with. And once I start the optimization process, it goes through all the design iterations automatically behind the scenes. And then end of the analysis, it actually tells us, here is the optimal solution. So it starts off with an initial design, baseline design that we just tested. And then we let optimization take over and tell us what's the optimal design. So you can see that the optimal design, the ribs are a lot thinner than the initial design. And the best news here is that if you look at the overall mass, we went from about 59.5 pounds to about 57.1 pounds, roughly about 4% savings in material. But think about it, right? Even if we can trim 1% material away from your existing designs, that could mean a 15% increase in profit margin, and that's money in your pocket, okay? Now, with optimization, it's not just getting to the optimal design, but you can also do what is called as the design sensitivity analysis, where you can understand if changing that particular rib thickness, does it really help the performance? So you can see that if, with respect to the rib thickness, how the factor of safety actually levels out So it's got an exponential reaction to that particular design dimension. But if I look at how the rib spacing, changing the rib spacing affects the results, you can see that the factor of safety is more or less like a linear response. So we know that the rib thickness is more sensitive towards the performance, in this case factor of safety, not so much the rib spacing. So again, additional information that can actually help you drive or test multiple design dimensions on your design. The local trend analysis or the design sensitivity analysis is another nice output or result that is given out by optimization. So what we did here was a quick optimization to find out the best design. Okay, so think about it, right? You might have all these different ideas in your mind. You want to test it, but again, today it may not be possible because it's going to cost you time and money. So optimization is a great way to virtually test all those multiple ideas and see which design is going to work the best for you end of the day. Now, what we're not still done here, what Forgeline wanted us to do was actually take this optimal design and test it for durability. How long is it going to last? Now, this actually goes in the race cars. Typically, we're looking at a 20 rally life. And so the next step was to actually prove out that SOLIDWORKS simulation can actually help them understand things like the warranty period and how long this wheel rim is going to last without any problems. So before we took a dive into doing that type of analysis, a couple of things that we wanted to make sure was the loading. So 2,900 pounds was the worst case scenario of loading. And this again happens only during a cornering situation. So this load is typically coming on and off multiple times on this particular wheel rim. And the goal was 20 rallies minimum without any issues, which translates into 150,000 cycles of repetitive loading and unloading of this 2,900-pound load on the axle. So again, that brings us to the concept of fatigue, which is a great way to understand, depending upon the working load, how long your product is going to last, especially if that load becomes repetitive in nature. So there's a lot of literature you can actually find online, like the mil specs, or maybe if you go to materiality.com or eFatigue, E as an echo, fatigue.com. These are great places where you can get information about, required for fatigue analysis on a particular material of interest. So to do fatigue analysis, it's the same workflow. It's not rocket science. We start off with the study process. Now, instead of static analysis, we say we want to do fatigue analysis. And there are two additional steps that you need to do here. One is telling the SOLIDWORKS simulation program what is the product cloud? What is the number of testing cycles expected? So that's an input, 150,000 cycles in this case. And then the other input is what's called the SN curve, which you saw in the previous slide. You can actually get that information from your material vendor, or you can actually go to those websites, efatigue.com, or you can actually look up a mil standard spec to get that information. Now, what we also offer as part of fatigue analysis and SOLIDWORKS simulation is, if you're working with steel alloys, the program has built-in ASME codes for deriving the fatigue information for that particular material of interest. So if you know that, if you're using a steel material, then we have some options built in. You can always plug in your own data if required for doing the fatigue analysis. So bottom line is, from a technical perspective, we call it the SN fatigue curve. Now, the results of the fatigue analysis are pretty straightforward. There are two key pieces of information that simulation gives us. One is visually it tells us where in the design, the fatigue is going to take place much faster compared to the rest of the design. So nice visual feedback on things. For example, on this wheel rim, you can see the ribs over here are actually going to fail probably first due to fatigue compared to the rest of the design. So that's kind of a quick visual feedback tells us which areas of the design we need to focus on. But we also get numerical feedback as to how many cycles are we talking about. So we want this entire wheel rim to last for at least 150,000 cycles. But the program comes back and says, look, you can do better than that. This thing can actually last 2x times, 2 times more. so that we are really in good shape. So a quick way to understand what the life of the product is using SolidWorks simulation. Now, what's the benefit of showing all these things to Forgeline, and eventually when they brought the software in-house, they were able to actually address the key challenges. Prototype testing was expensive. They were actually able to test a lot of these designs in-house using SolidWorks simulation, and it actually brought down the cost of prototyping by about 40%. Redesign and testing takes a lot of time. They were able to reduce that and knock that down by 25%. And competition is a lighter wheel rim. So they were able to actually go ahead and capture or recapture some of the market share by about 12% from the competition. And this is kind of a quick quote from the engineers there. We have reduced the weight in several of our designs while actually increasing the strength. So again, what is actually a serial process or a manual process Forgeline was actually following for many, many years? That process was actually, kind of compressed by bringing a virtual tool, SolidWorks simulation, in-house. And so being able to iterate virtually until the design and performance requirements are accomplished, and then finally make a prototype out of the optimal or the best design. So again, design the physical prototyping becomes now the last step in the process. And again, with SolidWorks simulation, they were able to predict and get a lot more information about the designs upfront in the design cycle. So the more simulation they did, the more questions they were able to ask themselves about the design, and the more questions they asked, the better design decisions they were able to make on this wheel rim assembly. And by the way, Forgeline actually makes a lot of these wheel rim, different sizes, different shapes, and they were able to use SolidWorks simulation on all these different designs, optimize, lightweight the rims, and have a better have that edge over the competition for the same similar design. But what this wheel rim demonstration hopefully showed you was how we could actually take a design today, initial to a better design, and we tested initially for strength, which is making sure that the operating loads are actually safe, and that you can do today with SolidWorks Premium if you have that particular package. But then what we did was we took the next step in the process to lightweight the design using Simulation Professional, and then also making sure that it's durable enough, it's going to last X number of cycles, or X, so making sure that it's going to last 20 rallies or 40 rallies and so on. So I'm going to actually, I had a slide for questions, but just in the interest of time, we'll defer the questions towards the end of the presentation. So I'm going to dive into the second demonstration for today, which is kind of a fun example. It's a stand-on riding lawnmower, and we're going to look at this platform on the lawnmower for safety, vibration, and comfort. So this is kind of a quick snapshot of a person standing on the platform, and this platform is literally cantilevered to the chassis, and so we want to make sure that it's going to be able to withstand the weight of somebody standing on it. It's not going to shake up excessively, and the person standing on it is going to be feeling comfortable riding the lawnmower. Okay. So this is what the platform looks like. It's literally cantilevered. You can see a couple of brackets towards the back of this platform, sheet metal, and that's actually bolted to the actual chassis. So we're going to look at how strong this baseline or the initial design of the platform is. We're going to check for vibration. So we're going to look at doing some quick frequency analysis, and maybe make sure that the frequency, the natural frequencies of this platform does not match the motor that's actually shaking up this entire platform, and eventually look at true vibration, where we want to make sure that the person standing on the platform feels comfortable enough. So let's start with the strength analysis. Again, a simple proof of concept that we're after is making sure the factor of safety is at least a 2.5 on the platform. So let's go back. Yeah, okay. So let's. I'm going to kind of go over the next couple of slides and then jump into SolidWorks to show you the model live in action. So we're after, a minimum factor safety of 2.5. So the initial baseline test actually shows us a factor of 2.58. And with SolidWorks simulation, you can also go ahead and, it's not just, working within the user interface, within SolidWorks all the time, but sometimes, you might have your team members working on the same project, but they may not have the tools on their machines, or maybe the scenarios where you need to share your end results with the client, or maybe something really cool, a nice, cool-looking animation that you want to share with maybe the sales and marketing teams in your company. So there are different ways in which you can actually share simulation results. The first one is, of course, looking at a detailed report. So this is, again, this might be part of your design process to actually create a detailed documentation of the simulation setup, results, and the model. So keep in mind that SolidWorks Simulation does offer you this reporting tool, and this is kind of a sample report that comes out of SolidWorks Simulation. You can see that it's very professional, it's complete by itself. It starts up with a nice table of contents, it captures the model information, and it actually goes through, being able to, it captures every single detail of the model as well as the simulation, what type of mesh was used, what kind of units, what materials, and you can see that it's a very professional report, and it includes all the results as well. Now, you can add things, delete things from this report to make it complete according to your design guidelines. But just keep in mind that, a reporting tool, instead of you cutting and pasting data and spending a couple of hours trying to do that, let the software do all the hard work behind the scenes for you. So eDrawings is another nice output. I'm just going to go ahead and show you the eDrawings file. There you go. So this is kind of the, when you can save all the simulation results in eDrawings format. And what is really nice is, this is a great way to collaborate and share information, again, with someone who may not have the tools. And in this case, I have all the results of the strength of the static analysis. I can look at stress, I can look at displacement, I can rotate, I can zoom in, I can do some markups, and I can look at things like factor safeties. All the simulation results that you are able to visualize within the user interface in SolidWorks, all those results can be saved into an eDrawings file. It's, again, a great way to share information, communicate information with people who may not have the tools. So I'm going to go ahead and quickly show you that model. I don't want this to be a death by PowerPoint. So here's the platform, and we can see that the brackets, this is actually the optimal design. So let's go ahead and switch this to the initial design. So you can see that when we start up the initial design iteration process, the two brackets are next to each other, and the results of that is going to be, in terms of strength, we're looking at stress analysis, the stress results, displacement results, factor of safety. It's about 2.58, like we saw before. The one thing I want to point out here is that, some of you might be wondering, how do we actually simulate that load, like the person standing on the platform. So earlier on the wheel rim, I showed you different types of loading, and distributed mass is one type of loading. So here, what I'm saying is, instead of modeling the complex human geometry and putting that person on top of this platform, we can simplify the process by using the distributed mass. So we're simulating a total weight of about 175 pounds that's distributed over these two highlighted faces. Okay. Now, if you look at the factor of safety, that comes out to be 2.5, which means that this platform can actually sustain a total load of about 400 pounds, anywhere from 400 to 450 pounds. So for a given 175-pound load input, the factor of safety is 2.5 times. Technically, that means that the platform can actually take on 175 times 2.58 load without any issues. Now, the frequency analysis is pretty straightforward. Again, you start off with the same process. You go ahead and say, I want to start a new study, and the type of study is going to be frequency, as simple as that. Okay. And then the results of the frequency, the way you apply materials and loads and fixtures remains exactly the way as you would do a linear static analysis, what I showed you on the wheel rim. But I want to actually point out a couple of things. So the results of frequency analysis are going to be, number one, it's going to show you what the natural frequencies of this platform is going to look like. And the number two option is, the number two result is what the mode shapes look like. So here you can see for a frequency of 36 hertz, this is how the platform is probably going to shake up. I can animate this in real time. It might be a little bit choppy over the internet connection, but then hopefully you get the idea. So two key pieces of results that we get out of frequency analysis is what are the natural frequencies, and the second one is visually you can see how the deformation takes place. So in terms of what we call as mode shapes. All right, so we did a strength test. We did a quick took a quick look at the frequency or vibration testing, and we saw the natural frequencies at about 27 hertz. That's the first natural frequency. But remember, we do have a motor sitting, inside the lawnmower, and that motor is rotating at a certain RPM. And if that RPM frequency, if you convert that RPM into frequency in hertz, that matches the natural frequency of the platform, then we have a big problem. So here we clearly see that the motor is operating at 1750 RPM. That translates into 29 hertz, and simulation is telling us the first natural frequency is 27 hertz. So we're almost in the same ballpark range as the operating frequency of the motor. So clearly we need to test for true vibrations, making sure that the motor is not shaking up this platform excessively. Just because things like resonance might set in and the platform might shake like crazy, maybe launch this guy standing into space, who knows. So we want to actually wrap this up by, first of all, understanding what the natural frequencies are, and then also making sure if those natural frequencies are in the same ballpark range as the motor, which is operating the entire lawnmower. So from there on, once we kind of establish if there are going to be any kind of vibration issues, then we go ahead and do a true vibration analysis. Okay, frequency analysis is really the first step. But before we dive into vibration analysis, one thing that we want to make sure of is the fact we want to see if there is any way SOLIDWORKS simulation can actually help us bump up the natural frequency of the platform. Okay. So again, we're going to take advantage of the optimization tools. And in this case, what we want to see is if we adjust the bracket spacing, currently the distance is about 6, as you can see on this particular slide. So maybe I'm thinking as a designer, engineer, well, how about increasing the spacing? Is that going to affect the natural frequency? So I can do that manually all day, but again, I'm going to take advantage of optimization tools within SOLIDWORKS simulation to automate the process. So again, all I'm doing here is I'm changing the distance between a range of values. And then my goal is pretty straightforward. I want to maximize the natural frequency, the first natural frequency. So that's a simple two-step process here when you want to optimize based on the frequency results. And the results of the optimization is going to be, the optimal design. You can see this plot over here clearly shows us the spacing is a lot different than the initial scenario. That's about 10.5 inches compared to 6 inches that we started off with. But notice how the frequency of the initial design changed from 28 hertz to 37 hertz. So that's really cool, right? We use a tool like optimization to kind of tell us if there's a chance we can bump up the natural frequencies, shift the natural frequencies to a higher frequency, and optimization did a fantastic job of doing that. Now, if you translate that 37 hertz into RPM, that's about 2220 RPM, which is far, far greater than the operating speed of the motor, which is 1750 RPM. But we still want to make sure that, the natural frequencies are not going to shake up. Sorry, the natural frequencies are still good, and the external excitation coming from the motor is still not going to do any, it's not going to break up this platform because of resonance and excessive vibration. So we're going to do a quick vibration analysis, what we call as harmonic analysis, and we want to make sure that the structure does not actually break because of resonance or load amplification. I'm going to skip the slide, but think about frequency analysis as free vibration, and then what we're going to do try to do next as true vibration analysis. We call that as forced vibration. Okay, so hopefully this particular slide showing the animation gives you an idea of what we mean by forced vibration. So think about, you might be testing your designs today using, according to a build spec where you are mounting the product onto a shaker bed table, and the table actually shakes up and down or sideways over several excitation frequencies. That's the exact scenario that we are actually going to simulate using SOLIDWORKS simulation. Now, the results of the vibration analysis it's very interesting to see what vibration analysis will actually help us out with. It is the way we set it up, run the analysis is exactly what you've seen before with the linear statics and the frequency analysis. But one of the key things of running a harmonic or a vibration analysis is being able to look at, how is the structure, how is the platform going to shake up under the multiple frequencies of excitation. So here on this XY chart on the left side, you can see that on the x-axis I have the frequencies of excitation, on the y-axis I have the amplitude, and this is showing us, for example, a center location on the platform, which is a lot red over here. So it makes sense to pick up or grab a location at the center of that platform and tell the program to give a response over at that location over the range of excitation frequencies. And clearly you can see that there is one big peak, and that peak is roughly about, let's say about 34, 35 hertz, and the amplitude of the center point is about 50 millimeter displacement. Okay. So that might be still acceptable. It's not a whole lot, but again, this actually gives me an idea as to whether the operating speed of the motor is acceptable or not. So the resonance takes place at about 2200 RPM, and clearly simulation is telling us, what the end effect of that is going to look like, 50 millimeter of displacement. And if that is acceptable, we can still let the motor operate in that RPM range. If not, this is clearly telling us maybe a safe operating range is less than 1800 RPM. Okay, so again, a great way to understand what might be the safe operating range of of this motor, if I cannot change the working RPM of the motor, then the next step is to try out maybe multiple design scenarios, different design cases, and see what design case is probably going to give you an amplitude that's acceptable. Maybe you're looking at keeping the displacement of this platform to less than 20 millimeters or 30 millimeters, and so SOLIDWORKS simulation vibration analysis can actually help you out there. So bottom line is we actually saw three different things on this lawnmower. We saw strength, we saw the frequency analysis, and then we finally also did a true vibration analysis. But again, the roadmap here was to go from an initial to a better design. So, but first, the fundamental thing that we did was to make sure that it's safe. We also made sure that it's comfortable. We optimized the design using Simulation Professional, and then using vibration analysis in Simulation Preview, we are able to take that optimal design and make sure that the stress, the deformation in the platform is still acceptable, and go from there. So the last example of the demo for today is going to be a little bit, we're going to switch gears. We're going to look at a desktop CPU enclosure using our flow simulation tool, and we're going to look at fluid thermal interactions. We're going to look at a couple of design or packaging options, and maybe with electronics, systems packaging. We are looking at using multiple fans. Maybe I want to look at if I can get away with 1 fan, 2 fans, or 3 fans. If so, what's the best location of those fans? That's exactly the value of flow simulation comes in, is to help you test and understand those multiple design iterations that you're after, so that at the end of the day you can actually optimize things like airflow patterns, make sure that you can make a trade-off between using number of fans versus noise and things like that. So the design challenge here is pretty straightforward. The first thing that we're looking at is, what are the key parts in the electronic system that needs to be kept cool? So, for example, the CPU, IC packages, RAM chips are all critical parts of this assembly, and they have a certain threshold temperature. We don't want those parts to actually exceed those threshold temperatures. And then based on that, we're going to look at a few design cases or scenarios, like other different packaging options. Can I try out multiple venting options on the enclosure? How about fans? Can I use 1 fan, 2 fans, 3 fans? If I can get away with 1 fan, what's the best of the optimal location of this fan? But the overall objective is to minimize the heat buildup in this entire electronic system. So we're going to look at 3 different things and how hard does it get. We're going to look at some packaging options and see what's the best packaging to go with, and also finally look at fan configurations. So first, let's see how hard does it get. Okay. Now, there are 2 ways in which you can solve a thermal issue on your design. One is an FEA approach, one is a CFE approach. The FEA approach here is, again, just like you saw linear static analysis, frequency analysis, you can actually do a thermal analysis. But the biggest thing that's going to make an assumption on here is what we call as convective heat transfer. So I can do an FE analysis, and I can start off with a convective heat transfer coefficient of 5 watts per meter squared Kelvin, and you can see the effect of that, right? When I look at the temperature distribution on this, all the parts in this sitting on the circuit board, you can see that it's way too high. These things are probably going to melt out. So what I do is, as an engineer designer, I would actually get an answer that's pleasing to me. So I change the convective heat transfer coefficient to 50 from 5, because that's still acceptable. So now I get into a situation where I get much cooler temperatures that's acceptable. And but what did I do just now? I just bumped up my convective heat transfer coefficient from 5 to 50. And there are plenty of numbers to choose in between, right? I can choose 10, 15, 25, 30, but which one is the right one? Well, the right one here is the one that actually gave an answer that I personally like, So we are making a big assumption when it comes to convective heat transfer analysis using FEA approach. So if you go online and just simply Google search for free convection air, you're going to get these values, 5 to 25, or forced convection could be 10 to 200. But again, the key question is, which is the right one to use, 10 or 200, 5 or 25? And I got a zillion numbers to pick in between those two, between that range. Now, so that actually brings us to flow simulation, because flow simulation, what I can do is I can simulate the exact physics without compromising on the performance. So here I'm just showing you a screenshot of a flow simulation. So it's got the same feature tree style as the FEA or the structural simulation that we saw on the wheel rim and the platform assembly. And we start off with what is called as the wizard. That's kind of the easiest place to start in flow simulation is the wizard. Here we're doing an internal analysis, but keep in mind we can do a combination of both, internal as well as external, which accounts for what's happening, outside of this enclosure as well. Now we can combine that fluid flow with some physical features, like simulate a little bit of multi-physics, where we say, all right, in this case, we want to account for heat convection effects, and so on. And then finally, we say, all right, the fluid I'm going to use is the air. And the good news is we provide you with a database of different types of fluids to choose from, and you can also custom create your own materials in flow simulation if the need be. And finally, we wrap up the setup by saying that a okay, these three holes on the right side are simply going to be exposed to ambient conditions, what we call as environment pressure. So that's a boundary condition that we apply on the three holes that are exposed to ambient space. And then we apply some fans on the inlet side. So again, instead of modeling the complex geometry of the fan, flow simulation actually provides a nice way to account for the effect of the fan by using a fan boundary condition. So you can see that there's a lot of information available in terms of being able to use a particular industrial fan right off the bat. So we have a database of different fan data that we have actually worked with local vendors to obtain information like the flow rate versus the pressure drop, as you can see here. And that's kind of the bread and butter of using a fan, is to be able to actually tell the program what's the relationship between flow rate and pressure drop for that particular fan that you're trying to simulate. And then we have some heat sources for different, for the RAM chips, for the IC chips, for so several other components on this circuit board that are generating heat. And finally, we go ahead and run the analysis. Now, one of the things I like about flow simulation is the fact that you can actually run the simulation on a remote machine and be able to actually continue doing something on your local machine. So that way your local machine is not frozen up while the analysis is running on a remote machine. Now, also with flow simulation, you can actually control the number of CPUs you want to use for a particular analysis. Now, also during the solution time, as the solution is cracking behind the scenes, it's not a black box to you, but in flow simulation, you can actually go ahead and look at what is happening, in terms of maybe the pressure, velocity, temperature. And here I'm showing you a quick screenshot of, how what kind of information you can monitor as the solution is running behind the scenes. And that's a great way to make sure that, everything is working as expected, because some of these things can actually take 30 minutes, 45 minutes, 1 hour, 2 hours, 2 days, 2 weeks sometimes to run. You don't want to wait that long and then realize something is not right. So then and there, as you're monitoring the solution, you can actually make you can make a decision if that's what you expect to happen. If not, you can stop the analysis, go back and maybe, revisit your design, revisit your boundary conditions, and things like that. Now, the effect of, using flow simulation is you're not making any assumptions on convective coefficient. The program is actually calculating that for us. And you can see that based on the actual physics, the right of the bat, flow simulation comes back and says the physical parts in the assembly are actually under the threshold temperature requirements, so we are in good shape. So whereas in FEA, you have to make all this, you have to probably try 5, 10 iterations to get to the answer that you're after. In flow simulation, you get that right off the bat. Now, like I said before, flow simulation actually calculates the convective heat transfer, and you can see that you can actually get a nice distribution of the convective heat transfer everywhere on the design, the geometry. And you can clearly see, for example, the heat sink, the convective heat transfer is not uniform or constant. You can see that it's a lot of red on the front end versus the back end is blue. So it kind of tells us that the convective coefficient is all over the place, anywhere from 0 all the way to 50. Now, again, one of the nice things about flow simulation is you can actually go ahead and take section plots. You can, you might be interested in analyzing a local area of the design where you can, you want to slice that area and look at maybe things like temperature, velocity, pressure, whatnot, turbulence information. So you can slice and dice your results using this section plot in flow simulation. One of the nice things about flow simulation is what we call as flow trajectories. And this is actually showing us, and hopefully it's not that choppy over the internet connection, but hopefully you can see how the air is coming inside, being sucked in through these fans on the left end, and how that air is being, how that air is moving inside of this enclosure. Okay, and so it circulates inside, and then it finally exits out of these 3 ports on the right side of the packaging. So it's a great way to understand, or optimize or look at airflow patterns. And because right in the bat, when you look at this flow trajectory animation, which is 3-dimensional in space, you get an idea of what is going on, where are the gray spots, where are the stagnation areas, is air trying to recirculate or just be stagnant in certain areas of the design. Am I getting sufficient air circulation around critical parts of the assembly, for example, IC chips, RAM chips? So that's the kind of information, visual feedback that you get right on the pad by simply looking at quick animation of the flow trajectories. You also have access to engineering data with flow simulation. So there's a lot of engineering information that you can output directly from the program, and this is just showing you a sample screenshot of temperature on different chips over here, the RAM chips, the main chip, and so on. And you can obviously take that result and export all that information into an Excel spreadsheet, and if you, in case you want to do further post-processing of that information. So bottom line is, we kind of seen how a quick comparison of FEA versus the CFD approach, and we flow simulation kind of it establishes that to predict the true thermal performance, thermal fluid performance, the CFD approach and the flow simulation approach is the best option. Now we're going to go ahead and look at some packaging options, and just in the interest of time, I might actually have to go through real quick, the next few slides real quick, and then hand it back to Dana. For packaging, again, we might have several design options. So one is completely solid enclosure versus, the enclosure might have some vents on the top as well as bottom. Now, if I run the analysis and quickly compare versus no vents versus the with vents, you can actually see that with vents, the temperature actually, the distribution, we start seeing some recirculation areas around the main chips. So without the vent, the flow is more streamlined, as you can see on the scut plot. But with vents, you can see those recirculation areas on the corners and also in the middle here. And that's not, something I'm expecting. So I want a smooth flow through the system, a more laminar flow through the system. I don't want to see these recirculation areas. So that's the value add-on of using flow simulation to test multiple design ideas, is to make sure that something that might look or seem logical may not be the case. In this case, venting, putting vents on the top and the bottom might actually give us an idea that, oh yeah, I'm going to keep the thing much more cooler, but it's not really the case here. Now, when I take a look at both these designs and compare the maximum threshold temperatures of some of the key components like the chips, the microchip, the IC chips, the RAM chips, and so on, and you can see that compared to the vented design versus the no vented design, you can see that how the vented design actually seems to end up with higher temperatures on the key critical parts of the assembly. Okay. And this is something, of course, both the designs satisfy the threshold requirements. Both the designs are okay. But when it comes to looking at the actual temperatures on the key critical parts, you can see that with the vents, the temperature is a lot higher compared to the design without the vents. So again, a combination of flow simulation and some of the electronics cooling can actually help you test your electronics design, and any issues you might have with thermal management, and where you're trying to optimize airflow patterns, optimize the designs, you can actually use a combination of both flow simulation and electronics cooling to get the job done. Finally, we're going to actually dive into fan configurations. Again, a lot of times, you want to see if I can, if you want to use 1, 2, 3, I can use 10 fans or 20 fans all over the place, but what's the trade-off? Well, added noise and vibration. So again, it's also important to see if you can get away with 1 or 2 fans, but then being able to see what's the optimal location of those fans that you can get away with. So in flow simulation, what we can do is we can clone the project instead of trying to set up the problem one more time. And cloning is a nice feature where, just like think about how you would actually reuse information in SolidWorks. If you're creating a new assembly, then you want to reuse some of the existing parts in the new assembly. That's the same concept here. It's called cloning in flow simulation. Now, what I can do also with flow simulation is I can set up all these different projects I want to run, and then I can simply batch run it at the end of the day. So I can pick and choose which projects I want to run in flow, and then I can go ahead and solve this on different computers of interest. So I can have multiple network machines. I can hand off each one of these analysis to a different machine, and that way I can get results for all of these analysis much faster. Now, one of the nice things about flow simulation is being able to compare the results. Okay, so here I'm looking at, there's a nice compare tool which pulls information, and using the compare tool, what we're looking at is for all the different design scenarios that we ran, we're looking at the temperature comparisons for some of the key critical components, and it does a fantastic job of pulling that information automatically behind the scenes and showing it in one single chart where you have all the different designs and the temperature results for each one of those designs side by side. And then, of course, you can take that information into an Excel spreadsheet for any kind of further post-processing. But here's what's happening. So here, what I've done is I've tested different design scenarios, just using one fan, on the left, middle, and on the right side, and then using two fans, and then changing the position of those two fans. And when I put all that information together, it obviously helps me read out, what design is insignificant. So, for example, design A is not going to work. So I'm going to quickly take it out of the design consideration. Design B is probably not going to work because it's exceeding the threshold requirements. Design C is also not going to work. A, B, again, I can take that out of the equation. So there are now, end of the day, I tested like 1, 2, 3, 4, 5, 6, 7 different design cases, and I can use flow simulation to test all those 7 cases because it's going to give me information that I can use to kind of weed out all the insignificant designs. So end of the day, I'm left with 2 different design scenarios where I have 2 fans and I have A, C, as you can see from this picture, and then I have also the option of using B, C. But which one is actually better to use? So I look at, if I put all the data for the temperatures for all of these design scenarios, then at the end of the day, B, C is actually the winner because it's much cooler. The temperatures with this design config of the fans, it's much cooler compared to the A, C design option. Okay, so both these designs actually satisfy the, our design, our threshold temperature requirements, but B, C actually ends up with a lot lesser temperature compared to the other design scenarios. So being able to test quick, all your ideas, and in this case, we tested, multiple fan options, multiple positions of the fan, and because we know that the lesser fans we use, it's going to reduce the cost, noise, and the energy usage, which works in our favor. So in this case, we started off with 3 fans, but then we ended up with 2 fans. But then we were able to optimize the location of those 2 fans. So we went from an initial better design using flow simulation, electronics cooling, and again, we tested 2 different things. Number one was to make sure that the critical parts are being kept cool, and then then the last couple of things that we tested was about packaging as well as the fans, number of fans we need, just to reduce cost, noise, and make it more energy efficient. It's sustainable. So what I want to do is kind of wrap it up and hand it back to Dana just in the interest of time. And there's a typo here on the slide. It should say 60 minutes. It actually should say more than 60 minutes, I guess. But I'm going to hand it back to Dana. But hopefully what you saw today makes sense. And because I know it is a quick overview, a rundown of the different simulation tools. But for a more in-depth demo of each one of the examples that you saw today, feel free to contact Progression Technologies and actually Hami can actually help you out with that. But now I'm going to actually turn it back to Dana, and he's going to wrap it up.
Sure. Great. Thanks, Ramesh. So we go back to our scenario talking about the GPS. Keep in mind that the GPS not only saves time but also saves money because you're not using as much gas, you're not using as much resources to get where you need to go. Same thing with SOLIDWORKS simulation. So from the money-saving aspect of it, I hope you get to see that using simulation upfront where changes are easiest to make and cost least amount of time and money, along with our automated features that come in the SOLIDWORKS simulation tools, gives you a really great way to not only have great design, but then also make and save money in the long run by taking this integrated approach moving forward. So in looking at some of the real quick, then we'll take some questions. We'll go to the next slide so we can say, you know, it's kind of one of those things, but wait, there's more. This is how the simulation tools are broken out. And so we'll go back to this. So you saw some things from Simulation Standard. You saw some tools from Simulation Professional, and you saw tools from Simulation Premium. This is going to be made available to you in your handouts that you can download. So I'm not going to go in these in detail, but you can see how the tools are broken out, what we call a good, better, best approach. So depending on what you want to accomplish and where you want to go, you have 3 different points of entry. There's no a la carte items. We just bundle them and price them accordingly due to the fact we try to bundle it all together. With the flow tools as well, same thing. You get to see with our flow tools the different types of things we do. You saw the flow simulation tool in action with the electronics enclosure, but keep in mind we do a lot more than just that, and you can see those tools there. As well as we have 2 extra add-on modules. If you're designing printed circuit boards, electronics cooling is the tool for you. If you're doing any type of advanced radiation, solar type of studies, anything going into space, HVAC, anything with large rooms, clean rooms, rack rooms, things like that, HVAC is for you. So you can see the 2 add-on modules. So again, that's included in your handout. One set of tools we didn't touch on, and this is another subject for another day, is plastics. If you're doing any type of injection mold design or plastic part design, again, the good, better, best approach. So plastic standard is for the folks who are just designing the plastic parts, and they want to understand the basic questions. Will it fill? Will I have weld lines, sink marks, air traps? Where can I put gates? Stuff like that. So you're just answering basic manufacturability questions. As you get into plastics professional, this is where you're helping design the best mold, the injection mold. How long the part should sit in the mold itself. Getting process parameters for the actual machine that's going to drive the mold, as well as different types of simulations depending on the types of molds you want to do. And then at the plastics premium level, we answer the ultimate question: will my part work? And if I keep my mold at a certain temperature, how do I do that with cooling lines? So that's the 3 sets of simulation tools we had. You got a taste today of the simulation tools and the flow tools as an idea of some of the things we can do. So with that, we'll give you guys a chance to ask some questions. Feel free to type them in the questions into the questions field. And while we're doing that, I'm going to address the issue of that customers always ask us all the time, and that is, hey, you guys are SOLIDWORKS. You're a CAD company, talking about simulation. How good are these tools? How accurate are these tools? I get asked that a lot, and the answer is, we run the same exact physics underneath. Physics don't lie. That's kind of Ramesh's saying. The physics don't lie, and because of that, we run the same algorithms, the same type of Boolean functions and matrix algebra. All the things the engine underneath that needs for the calculation is the same as everybody else out there. We have the same type of meshing tools. Everything that everyone else has, we have. They're kind of industry standards. And so in terms of accuracy and all that, we come right within lab data as well as our folks in our market space. In terms of what type of problems we test against, because we get that too, within our simulation tools in the tutorial, there are different types of problems that are given to us, standard textbook problems. Also, we get problems from an organization called NAFEMS. It's an organization based solely on the successful use of simulation tools. We are a sponsor along with a lot of folks in our market space, and their job is to make sure that the simulation tools out there are of the best quality. And because of that, they give us a lot of problems to test with. Those are also included in the tutorial. And speaking of tutorial, it's just what it is. It's a very comprehensive tutorial that's going to walk you through every aspect of whatever you're trying to accomplish with the simulation tools. It's a great place to start. We have a lot of, again, automated features, automated tools that's going to help you not only understand the simulation tool, but also on your first or second pass when you're just trying to get down the road, turning on the GPS and it's let the software guide you, because it knows how the model was created, because you are built in one environment with SolidWorks. And then another question we get all the time is, what kind of system requirements do I need? Is this a special machine? Do I need a true workstation? And the answer is no. If you have a 64-bit, 4 gigabytes of RAM, solid state hard drive is very nice, but you don't have to have that. But it's just the standard stuff. If your SolidWorks is running successfully on your machine, then our simulation tools will run successfully on your machine. There are exceptions all the time, but the good news is there's no special hardware to buy. There's nothing out of the ordinary per se. The more RAM you can afford, the bigger hard disk you can afford. That always helps. The more beefier your hardware, that's the better off you are. But be assured you don't have to buy anything special or order anything special. You can go to the SolidWorks website, and all the recommendations for video cards, disk drives, static drives, everything you needed is there, and those apply to simulation as well as the SolidWorks design tool. So with that, those are kind of the two questions I get all the time, and I want to make sure those get addressed. Are there any other questions from our audience that we can answer? Again, we showed a lot of stuff, just a taste of everything. We showed how simulation can be shared not only in a report, but also in e-drawings. So if you have e-drawings, you're into e-drawings, simulation results go into those very nicely, as well as the automated reporting features of our tools. So any other questions from our audience that we can answer for you?
I see one question, Dana. Can simulation results be shared in e-drawings?
Right, and the answer is yes. I just mentioned that. In addition to our automatic reporting capabilities, you can, and Ramesh showed some of that as well, that you could export that out into an e-drawing, any simulation result. And that e-drawing can be shared, marked up, whatever you want to do with it. It is free. The e-drawings viewer is all free, and so it's great to share with folks who do not have SolidWorks nor simulation for them to look at everything. Okay.
Excellent. I really like those presentations. Thanks, guys.
We have one more.
Oh,
hey, we just had a question pop up. What level of experience is needed for simulation in order to effectively use it? That's where progression comes in. We do have, I mentioned earlier, the tutorial. We do have some automated features, some wizards, all that. That doesn't replace training from Amit's team at Progression. For you to sit and learn the tools, a typical training is how long for the simulation tools, Amit, if you're doing the simulation and the flow?
Yeah, for simulation standard and professional, we bundle that up, and that's a 4-day class. And it's very not intimidating. We walk you through just a little bit of the theory, trying to help you understand how the program thinks, and then you understand what inputs the program is looking for. So you don't need any kind of FEA background. It's very easy to drive, and we're here to support you and help you with that. So yeah, that. And then flow, I believe flow is 3-day class, maybe?
Yes, it's 3 days. It's 3 days.
Okay.
And the same thing, it's theory, and then you learn the tools. And of course, Amit, you guys will provide on-site training, custom training, if that's what's needed.
Yes, yeah, and a lot of this, these specialty classes we like to tailor to our customers. So we would like to know, what suits your schedule. Do you want us to come out on site? Does this certain month work better than another month? We schedule that tailored to you. Where some of our other classes, those are, on a monthly basis, but we design the specialty simulation classes for the customer.
Okay, great. Good. Okay, are there any other questions for us? Going once? Going twice? All right, sold. So, Amit, if you want to take it from here and thank everybody, and I'll let you close out.
Yeah, thanks all of you for attending. For me, I love that this presentation really showed how simulation takes some of the guesswork out of our design process, with the vent design and the rim design. There's some of those things you wouldn't have been able to predict without the assistance of the software, and that's what it's for. It's for you using that toolkit to help you navigate your design process in a faster way. So definitely, if you have any questions, let us know. We want to help you, achieve your goals um, and progress through your projects as well. So you can send us an email at support@progressiontech.com. Any feedback you have on the presentation can go directly to me or to support. My email address is AMEE, at progressiontech.com. And thanks all of you for attending.
Yes, thanks everybody. Everyone have a
Thanks,
great day.
Tommy. Thanks, Dana. Thanks,
All right.
everybody.
All right. Bye-bye.